Yeah, the questions like to like we didn't have to do all the questions, right? It was only seven. So like we need to we need to look at those or like solutions to those things or whatever.
Oh, yes.
We do. So let's see.
Did you ask about homework 3?
Yeah, no, I was just saying for the homework, the questions on homework three that we
Yes, yes, we talked today. Yes, we
think about it. No, I'm just saying like because
Yes, you have enough time and we talk today. Yes.
no, I was more saying like because we on whichever homework was due last night, we didn't have to submit answers to all the questions, right? It was only seven.
Ah, yes, yes, yes. That's
Yeah, so I was just sort of wondering like what do we need to do with the questions we didn't submit solutions to? Like,
you can read it. Yeah, yeah, it's for you. Yes, yes. You know, it's best to study it. Yes. But you don't have.
Like, is he gonna? Do you think he's gonna use any of your questions on like a test?
No, I can't know, but you know, if you study more, it's better. But if you have final source of time.
Like some of them were like a card one. I thought for sure I'd do that one.
That's okay. That's okay. Good question. Okay. As good morning, everyone. Let us start. Today we recitation number 4. There are no new homework this week. You need to submit homework number 3. Okay. And today we continue with materials from the previous lecture. And we'll talk about a couple of questions, couple of ideas that can help you to solve homework number 3. So today we're here. There are no new homework, as you can see. Okay, and today I will use this old slide, but you also can use new slides, but I will use old slides. Okay, so this is our slides. Let's open it. And let's start the talk. Okay, so today, just let's close this guy. Yes, okay. Yes, we should be. Okay. Okay, so today we will talk about distribution function, about quantile function, and also we will see some application of quantile function. We will see how we can generate exponential random variable from uniform random variables. It's a very important trick. Why? Because it's very useful in data science and statistics in simulation. In many situations, we need to generate random number from some distribution. Normal, Fisher, T, geometric. But computer basically can generate random numbers from uniform distribution. And today you will see original approach, how you can generate, for example, exponential random variable from uniform. We also have something similar in your home. Okay, this is very brilliant idea. It's a very useful idea, so we will solve it today. And as I said, it's very useful, for example, in simulation, in Monte Carlo simulation courses. Okay, this is one of applications. Okay, so let's start. Okay, this is a reminder about random variable. Okay, this is our guest for today. Distribution function. Do you know this guy? Yeah. Okay, so very, very important notion. The distribution function of multi-distribution function, capital F of x, and the definition, it equals probability with random variable x less equal. Okay. This is very important notion. Why? Because it's useful. As you know, we have many kinds of random variables. Yes, discrete random variable, continuous random variable, singular random variable, yes, and the union of each one of it. And this, for example, discrete random variable we can define by the probability distribution function. Yes? And continuous random variable we can define by density function. But all of them we can define using the distribution function. But it's very, very useful. It's a good guide. Okay. In some cases, we can't find expression for this case. In these cases, we use tables. For example, for normal distribution, we don't have exact analytical formula for distribution functions. but we have tables, calculators, computer. Okay. So, what is the property? What is the property of density of the distribution function? Let's say a couple of them. First, its limit, yes, when x goes to minus infinity, f at this point x equals 0. Probability that x less equal minus infinity is 0. And from the second side, when x goes to infinity, fx equals 1. Yes, it's a basic properties. But you know, there are some random variables such that f infinity is not 1, is less than 1. Surprisingly, yes? Why is that? How it can be possible? Okay, the name of these random variables is defective random variables. They're defective, what can I do? But sometimes they are useful. But for our course for today, these are the properties, okay? But there also exist defective random variables. Oh. The second property of M. Okay, in Ori's note, he says it's monotonic increasing, but in more exactly it's monotonic not decreasing. Yes. It can increase, yes, horizontally increase, so more precise to say it's not decreasing. And distribution function also continues from the right, so limit of f x plus t is some positive number, converge to fx for every t goes to 0. These properties define distribution function. If you have some function f such that property 1, 2, and 3 hold, that can be distribution function. Okay, now we have question. It's a bit similar to some of question in homework, but it's okay. Here we have two assertions we need to check. We know that f and g are distribution functions. We know that lambda is some number between 0 and 1. And we want to check if this value is a distribution function, and also if this guy is a distribution function. In homework we have something similar. Okay, it's not very important question, but it's a question according related to the definition. So, question is clear? The question is clear? Okay, well, what we need to do, what is enough to do? Enough to check the definitions, yes, to prove at least 3 properties. Okay, so let's check it together. Okay, let's denote this guy by hx. And our goal is to check.
What it was?
Hmm?
What was the notation?
Hx?
H.
Hx. And I want to check with hx. For hx, all these properties hold. Yeah. Okay, let's check it. Okay, this one. Okay, let's start. For example, we need to check the limit when x goes to minus infinity, hx equals 0. Okay, question mark, we don't know, we need to check. Do you agree?
Yeah.
Okay, now we need to substitute. It equals limit x goes to minus infinity, lambda f(x) plus 1 minus lambda. Make sense? Okay, now we will use many properties of limits from calculus. Okay. For example, limit of sum, the limit of sum equals to the sum of limits. Yes, limit of sum equals sum of limits. By properties of limits of lim, we have here limit lambda fx, x goes to minus infinity, plus limit 1 minus lambda jx. Make sense? Okay. Can we move lambda outside and 1 minus? Well, yes. Why? Again, rules of limits, properties of the limits, yes. It's no result. If we have function, product of function with constant, we can move the constant outside. It's the basic properties of limits. Okay, so it equals by properties of limits, lambda limit equals to minus infinity fx plus 1 minus lambda limit equals to minus infinity. Okay, what we can say about this fellow is about the second type. That's it. Yes. Fx, capital Fx, is a distribution function. So limit equals to minus infinity, fx is 0. It's a property of distribution function. So this fellow is 0. Also this guy. Okay, 0 times something equals 0 times something equals 0. So we check and we demonstrate it with h of x. This guy, h of x equals 0 when f goes to minus infinity. Make sense? Well, it's a basic definition.
Just for that
Yes.
second line.
Second line, yes.
Limit of lambda fx plus limit of like the parentheses of the limit are over the g.
Yeah, yes, that's
right.
Yes.
Yeah.
You're right. And now we move constant outside because it's a basic property of it. Yes.
Just move from the limit x goes to minus infinity of hx directly to the last line and says by properties of limits.
Yes. But
Just like plug in the minus infinity inside of f and g and says.
But all of these steps are necessary. But if you solve them, you can move from this line to this line. But if you want to understand better, you need to write all of them.
Yeah, I'm asking about the tests and quizzes and homeworks.
This is the perfect. Okay.
And just to write by properties of limits and.
If it's correct and if you understand it, but yes. But don't do something such that. First line we given and second line we answer. By the properties of limits, property of random variables, properties there, answer. No, it's not good. You need to explain. But here you can.
Here, exactly.
Yes. Okay. So we demonstrated that this guy equals 0. What we can say about this fellow? Similarly, yes.
Yeah.
Very similar. Okay. So similarly, we got that f it's x and x goes to infinity, h of x. X equals. Okay. Yes. I need to remove that. Okay. Property 1 false. Next property. We need to check that f is monotonic not decreasing or monotonic increasing function. Okay. Look. You can prove this statement using the definition of monotonic function. You can, but you don't need. You don't have. Why? Because we have some useful properties. For example, if f is a monotonic function, if f is a monotonic function, and lambda is a constant greater than 0, then lambda f is a monotonic function. It's very basic property. You don't need to prove it. You can, but you don't need in our course. Yeah. Okay. So if f is a monotonic function and lambda greater than 0, lambda f is also monotonic function. Okay. Increasing. Yes. Okay. And if second property, if f is a monotonic increasing function and g is a monotonic increasing function, then again, f plus g is a monotonic increasing function. Sum of two monotonic increasing functions is also monotonic increasing function. If you want, you can prove it, but you don't need. In our course, in calculus course, you need to prove this. So we'll use these properties to demonstrate the second statement, to prove the second statement and the third. And the third. Okay. So h is a monotone increasing function as a sum of monotone increasing functions. It's enough to say.
Wait,
Yes.
but why it's absolutely true?
What?
It have to be between zero stay as monotone is increasing.
No. If you have two, okay. Statement 2, we only need to check if h is a monotonic degree. Yeah.
Yeah,
Okay, sum of two monotonic degree functions, monotonic degree function.
but how we prove that lambda f is monotonic increasing? It's monotonic. Yeah, but why not decreasing? You know, if
Because
we
lambda is
with-
positive. Lambda is positive.
because
Lambda is positive. If you
Just
have some
because it's
increasing
positive.
number, some increasing function, and you
okay.
multiply it by some positive number, it's staying here.
But so it's we have to write it on the 1 minus lambda. That the lambda is between 0 and 1.
This lambda, yes.
Yeah, not just greater than 0, but also less than 1.
Yes. Yes. We use it. Yes. If lambda is 2, the statement can be incorrect. Yes. You're right. And if you really want, you can prove this statement. You can prove that it's monotonic discrete. But in this case, you need to say, let's choose two numbers, x and y, assume x greater than y, and let's prove that hx greater equal hy. You can prove it, but it's not necessary. Okay. So we can prove this second statement using the properties of monotonic function. It's enough. But if you want to check, you can. Okay. And the third step to prove that f is continuous from variety, we again use the properties of the function continuous from variety. The sum of function that continues from variety is also continuous. So it's okay. So this is the statement. According product, you can check it, you can do it. It's very similar. And in homework, you have some additional exercises according to this value. It's clear? Let's look on this exercise. We won't solve it until the end, but we want to understand the idea of its solution. It's from the lecture notes, from Oris notes. Okay. Here we want to provide an example for two random variables, x and y, such that probability that they are different is 0. So probability that they are equals is 1. But there are infinitely many points in sample space such they are different. So these two random variables are different in infinitely many points. But probability that they are different is 0. Okay, we only need to provide an example. Okay. Can you give me some example?
Maybe solution normal solution.
Normal, it's okay. Okay, normal and
one random variable will describe psychometric rates. The second, I don't know, the weight of.
No, they will different. You want. Okay, let's start from uniform, but you can use normal. You can use weight because you want. Okay, we want two random variables such that probability with weight not equals is 1. Yes, it's the same. Let's start from x uniform 0, 1. It's simple. Oh. If we choose y equals x, is it solution to this question? Y equals x. Okay, let's see. If I is x, the probability that x equals y is 1. Yes, the statement is false. Yes? But in how many points there are different? In 0 points. Because it's the same random variable. So it's not solution. So we want to change what? we want to change y in such a way that probability that x equals y is 1, but x equal to y of omega pointed to number of points, for example. So we want to change something. Okay, let's change. Let's define y of omega in this way. Y of omega equals x of omega if x is irrational number. What does it mean, irrational number? It's not rational. It's not irrational. There are infinitely many irrational numbers, but it also infinitely many rational numbers. So it's not so cool. But there are much more irrational numbers than rational numbers. If you choose some point from uniform distribution on the interval 0 to 1, with probability 1, we will get irrational numbers. There are so much irrational numbers, so we almost surely will get irrational numbers. So the probability that we get rational number is 0. Yes, we can prove it using the definition of Lebesgue measure, yes. Okay, so we define y of omega in this way. Okay, y of omega equals equals x omega if x is irrational, and y equals, for example, 10. I know 10 if else otherwise, yes, x is rational. Okay, now we can prove, but we won't prove that this is a good example for this statement. With probability 1, x and y are the same number, because the probability 1, when we choose some number from this interval, it will be irrational. But x and y are different in infinitely many points. Why? Because there are infinitely many rational numbers in interval from 0 to 1. And if you want to understand why, if you don't understand it here clearly, it's not easy question. You need to read more about set theory. Okay, it's usually students in mathematics studied it in set theory course. Yeah.
X gets rational numbers, right?
X
But
is a random variable from uniform from 0, 1. It can, yes. But probability what you will get rational number is 0. It's possible, but probability is 0. For continuous random variables, it's a bit counterintuitive. Probability, you can get rational number, you can, but probability of any rational number is 0.
So it's not discrete nor continuous.
No, it continues. X is continuous. It's continuous. It's uniform 0, 1. You can get any number from interval from 0, 1. It's continuous. But if you want to find probability that your final result is rational, it's 0. But at that moment, but pay attention. In application, if you use computer, you can generate infinitely long number. So if you will generate this random variable on computer, you always will get rational number. But it's an application. In the theory, you must get rational number with probability 1. Yes. Okay.
It's more general question. I know that for P, to calculate P, the probability is the F function, the distribution function, right? Yeah. So in continuous variable, it's the interval between minus infinity to the
X. Yes.
X. So if I take, for example, normal distribution, we know the density function, and the density function have the mean over there. Am I right?
What it has?
Mean.
Okay.
Yeah. So what I would like to know, if I will take two random variables like weight of people and the heights of people, it will be suitable for this question. The probability of the x not equals to y will be 0.
No, why? Let's see. X is a normal, mu sigma square, yes. And y is also normal. You want the other parameter or this one?
No, I guess it will be different.
Okay, mu1 sigma 1, mu2 sigma 2. Okay,
And then I'm asking about
probability that x x equals y is 0 for this case, and you want 1. If you have two unrelated random continuous random variables, the probability that they are equal is 0.
Okay.
Yes, because it's in general singular random variable.
So there is an example of real situation that this exercise come to life. I mean, for two random variables that not the same, which is the probability.
For two random continuous random variable, probability that it's not same, probability that equals is 0. As this controversial.
Okay.
And this exercise following the statement in Ori notes, and he says if for two random variables fx equals fy or something like that, then x equals y. It's continuation of theorem from notes.
Yeah.
Okay. So please pay attention. Thank you for question. This is it's not intuitive fact. It's very deep fact from set theory and from measure theory. But as example, we can understand it. But if you want to understand it deeper, you need to read about measure of rational numbers. And here you need to use Lebesgue integral, CTS integral. It's hard work, but as idea we can understand.
And just that's a 0. So that one, like right, y of sigma is x of sigma if at n 0, right? Is that a 0?
10 or 0.
10? Okay.
Yes. Any number.
Number?
Yes. What is the case here? For any irrational number, these guys are the same.
Yeah.
But for any rational number, they're different. Okay, that's all. You can use here. So it's a good example, and if you want to understand it deeper, you need to read a bit more. Okay. Okay, this is our next guest for today. We need to understand the definition of quantile function. It's a bit cumbersome, a bit messy for many of students because it's not so intuitive. Why it's not so intuitive? Because we have here this guy, yes, kind of mean. Okay. So let's define it. Let's demonstrate how we can use it and solve some two useful exercises if we have enough time. Okay. So quantile function. First of all, quantile function, this guy is very useful in statistics. We will talk about statistics next semester. It's very useful, but we need to understand. Okay. But in our course, we define it. We will demonstrate its properties of a couple of exercises, but you will use it more deeper in statistics. So this guy is for statistics in general. Okay. This is f is a distribution function. Okay, we know it, we demonstrated it's useful. Now we want to define inverse of distribution function, but it's impossible, in general, it's impossible to define inverse of f. Why? Why it's impossible in general? If f is monotonically, strictly increasing function, if it's always increased, something like that, but always increase from 0 to 1, in this case, we can find and define inverse function.
That's a continuous variable.
Because it's continuous and it's strictly increased. Yeah. It's one-to-one correspondence between x and fx. So in general, here it's very easy to define inverse function, and we will demonstrate it in the next slide. But for example, for discrete random variable, the distribution function has this form, step 4. Yes. This is distribution function for discrete random variable. And as you can see, it's not a one-to-one function. In this case, you can define f minus x as inverse function because inverse function does not exist. So we need this messy definition that always works. Okay, so let's try to understand. So the quantile function is a kind of inverse function. It's not inverse function. It's kind of inverse function. We will try our best to define inverse function of distribution. And it's defined in this way. You see, this is a notion, f minus 1, but it's a bit counterintuitive because it's not an inverse function in general. Okay, it's a minimum infinite, it's a minimum t, f minus 1 at point x. It's a minimum t such that ft greater equal x. What does it mean? Suppose you choose here x, some number. There are infinitely many points t, there are infinitely many, such that ft greater equal x. From all of these points, it's a set of points, we choose the smallest one, infinitely smallest one. Okay, so this is the definition. And let us use how, let me demonstrate you how we can use it. Okay, first, if we have continuous random variables and distribution function is strictly increasing, yes, x, fx, we can go in the cyclic direction and we will get inverse function. So in this case, we define quantile function as inverse function. That's all. This is the easier case. Okay. For example in the next slide. Okay. Okay. Let me show you how we can find quantile function for continuous case. Okay, let us use this jumble distribution. Do you know it? Do you know it? No. Okay, but okay. This is this distribution function of jumble. You can check in minus infinity is 0, in infinity it's 1, it's continuous from the right, it's increasing function, so it's properly defined distribution function. And now let us try to find quantile function of this field. It must be easy. Why? Because it's continuous random variable. It's not always easy. Sometimes we can't invert this equation. But in this case we can. So let us try to find quantile function for this field. So you can. So this is our equation. Let's denote it by u. U, yes, or p in this case. P equals e power minus b. So this is distribution function. We want to find inverse function. How we can do it? Yes, our goal is to isolate x. And to isolate x, we can do ln, and we get x. Yes. Pay attention, it's not always possible. If you have some equation, something like this, p equals e minus x squared ln x sinus x, I don't know. In general, we can't isolate x. It's impossible. So it's continuous function. We have equation, but we can isolate x. We can solve it analytically. Numerically, we can build table for every number. Yes, approximation. But we can, in this example, we can't isolate x. But here we can. So let's try. Okay, ln e equals minus e power minus. Yes, we can move minus in this direction. And what is the next step?
Again,
Yes. Ln minus ln p equals minus x.
and then we'll do minus.
Yes, we move minus to this direction. This is quantile function for jumper distribution.
Just algebra useful.
Yes, just algebra. But in many cases, f is hard expression and we can't isolate x. And we use approximation and tables. For normal random variable, we can find quantile function only numerically. But for this guy, we can. Is it clear? Okay, let's try something additional. Today we talk about exponential random variable. Let's find it quantile function. Suppose x has exponential distribution. You talk about this guy or remember it from your study, or you don't remember? with some very useful random variable. And this is the distribution function of x. It equals 1 minus e power minus lambda x. And again, let's find quantile function. What we can to do, what we need to do, similarly to this
Let's denote the function by p.
Yes.
And move the one to the other side.
Yes. Okay, that's the moment. You are right. Thank you. So p, we move
Yeah, it's more
Yes,
and one minus
minus e power minus x equals p minus 1. And minus here and here, e minus lambda x equals 1 minus p. Yes? And now ln minus lambda x equals ln 1 minus p divided by minus lambda. This is quantile function. Again, it was not so hard because it's easy distribution function. It's easy, it's clear. Excellent. Okay. Please read this explanation at home. Maybe now. This good explanation if you want to understand better the general case. Yes, we are, as you can see in plain English, we have an explanation of the expression. Oh. So, as we said, not every function has its inverse. So we need to define quantile function in this message. And what does it say? Let me repeat. For any given number p, there are many x's such that fx greater equal. There are many, it's a set of such x's, and we choose the smallest one. This is a definition. And if you want to see it in the picture, so this is the demonstration. Let's see what we have, what we can see here. Okay. Look, this is a distribution function, and this guy is quantile function. Distribution and quantile. Okay. From this picture, from the left-hand picture, what you understand? Is it continuous random variable? Is it discrete random variable, or is it a mix of discrete and continuous random variable? It's a kind of, yes. This random variable is a mix. It has also part of continuous random variable and parts of discrete random variable. Yes, it's a mix.
For example, the green part is the continuous variable.
Yes, here in this, yes. And also the yellow and also the pink. Yes. Yes. So what you can understand from the left picture? From 0 to 1 is continuous random variables. It's the distribution function is strictly increased. And in this case, the quantile function is inverse function of this guy. Okay, here we have a point of discontinuity. It's same for every point. Here we have a point of discontinuity. As you can see, in quantile function we have here, we don't have here anything. And if you want to know what is the value of quantile function of this point, what is the value of quantile function of this point? Yes, there are infinitely many points from 1 until infinity, such that fx less equal than these points, and we choose the smallest one, the left one, and the one. Yes. So for this interval, the preimage we can say is here.
Which variable describes this interval? Discrete?
No, it's the point of discontinuity. You can't get any value for this point. It's discontinuity. Here again, discrete random variable we have here and here. Here again, we have the interval where our random variable is continuous. So distribution function is strictly increased, and this is a quantile function. And here you see we have a jump. In this point, we have probability mass. So this is kind of discrete for, yes, probability discrete random variable. For this value, I don't know, that 2.6, the probability that this random variable will get this value is not 0. It equals this value minus this value. Yes, so this point has probability mass. And for this here we have a quantile function defined in this way. And we continue. So as you can see, it can be a bit messy.
So the yellow part, the above yellow part on the left.
Yes.
Yes. This is this discrete variable
No, this is again its continuity.
again.
Discrete variable, it's here, it's here. It's right because it's white. It's white. Yes. This is discrete.
Okay.
This is discrete, and this is points of discontinuity.
What
Yeah.
we are looking about. So
I was gonna say the colors are confusing because the first yellow
Yes, it's for this guy.
but it is continuous.
Yeah, yes, this is continuous. Yes. Now this
And then
yellow
the
is
second
equal.
yellow is not.
Okay, yeah, okay, you're right.
Yeah,
Yes,
yeah.
yes. So this continues. This is the point of
Yeah,
discontinuity.
the
This continues. This is discrete,
discrete.
continuous, point of discontinuity. We continue this.
Yeah.
So, okay, well,
I'm just looking at from the interval between 1 to I don't know 1.5,
yes.
and it looks like that's like the left row.
Here.
No, left one. On your home.
Left one. This one?
Left on your home.
Okay, yes.
It
Okay.
looks like a discrete variables. Stairs.
Okay, okay. Yes. No, yeah. Okay. This kind of random variable, let me draw it. From 0 to 1, it's continuous.
Yeah.
Yes. So you have some kind of.
It's like why.
Okay, I can draw it. Yes. You can't get any value from this interval.
Yes.
Here you can't get any value. It's impossible.
Why is that?
The probability is 0. You see, the probability mass does not change. The distribution factor doesn't change. So probability for every point in this interval is 0.
Okay.
Probably you can get it, but the probability is 0. And now again, probability distribution factor increase. So you can get any number from this interval.
That's fine.
It's also increased here. So you can get this number with probability equals the density function, the distribution function at this point minus distribution function at this point. So this mass of this point. And this continues. Again, you have jump. In case of jump, this point has probability mass. And probability mass of this point equals density of this point minus density in this point. Again, you can't get any, you can get some number from here, but the probability is 0. So you don't have here any increase. And again, you have concrete increase. And it must go to 1. Yes, finally. You see, okay, here for 1. It's okay. Yes. Okay, how would we have enough time? No. But let me to explain you something important. Okay, this last exercise for today. Pay attention, it's application. When I was a student and I saw this example, I don't understand it. I don't understand why it's related to our material. Yes, because it's application of something that we study. But it is very, very important application. Okay? So what is the idea of this question? And you need to continue this question in your homework. The idea is very useful in computer science, in mathematics, in statistics. The idea of the next one. You have computer, and computer know how to generate uniform 0-1 random variable. It's not a true. But we assume that it can. We call to these numbers pseudo-uniform numbers, but we assume that computer know how to generate this number. And now our goal is to generate random variable from exponential distribution using this guy. Okay, we want to write a function that use uniform distribution to generate random variable from exponential random. And you can use, you don't need to use exponential, you can use whatever you want, but in this example, we want to generate exponential random variable. How we can do it? And very famous theorem says, we can prove it now, but probably prove it in the lecture. Okay, our goal is clear. We want to generate exponential from uniform. And in general, we want to generate geometrical from uniform, Poisson from uniform, whatever you want, whatever is possible. Okay. It's a very interesting theorem that says if x is a random variable with some distribution function, and u is a uniform 0-1 random variable, don't, okay, U is uniform 0, 1 random variable. You can generate uniform random variable. We said the computer can do it. And now on this guy, you can apply any transformation, any function, yes? Function of random variable, measurable function of random variable is also a random variable. So we want to take this fellow and apply on this guy f, capital F, distribution function of x. That's all. And this theorem state that this guy, it's random variable, yes? This random variable, function of random variable is a random variable, has distribution of x. Okay.
Here is what?
Just a moment. Till I want to see f minus 1. Okay, wait, minus 1 has a distribution fx. So this is the theorem. When we apply quantile function of uniform and we get random variable that has distribution of x, this is our goal. So this is the algorithm. You generate uniform 0, 1 random variable and apply on it this transformation. That's all. Why it's correct? Okay, this is a statement. We need to prove it, but it's a statement for the lecture.
So you're using the quantile function to move from the uniform
For exponential.
exponential.
Not only for exponential, I also can use it to generate Poisson geometric. For normal, it's not useful because normal does not have analytical quantile function. But in general, yes, one of usefulness of quantile function to generate one random variable from uniform. Like it's very useful, yes. So this is what we need to do. We need to find quantile function of exponential random variable, but we did it today.
Yeah.
And apply it on U. That's all. Okay, why it's correct? We prove you need to check. Okay, to see.
How does it look like to apply it to you?
You see. I also have code in R. Yes, you will see. Apply some function sinus. You get U and apply to the sinus. What you say? Let's solve the question. Okay. So first goal is to find quantile function for exponential random variable. Yes, but we did it today.
Yes.
So this is quantile function. Okay, no, this is the question we need to solve. This is quantile function for exponential random variable. Now you generate uniform zero random variable. You make 1 minus e. It's easy. You apply ln. You divide it by minus lambda, and you get result. This result has exponential distribution. Why? According to this theorem. So this is algorithm how you can generate exponential random variable from a unit. One improvement here, small improvement. If U is uniform 0, 1, what you can say about 1 minus U? Intuitively, without proof.
0 to 1.
Also uniform. Something uniform from 0, 1, if you make vice versa, symmetrical versa, it's also uniform. So you can remove 1 minus. You can use uniform. You need to prove it, but in general, instead of 1 minus U, you can use 1 minus. You can use U. It's not big improvement, but it's small improvement from algorithm.
We're changing the mean of the distribution, like we are moving it to the left or to the right.
You use this transformation. Yes, if x equals 1 minus fx equals 1 minus x. Yes, these are kind of transformation. 0 goes to 1, and 1 goes to 0. It's symmetrical by half.
In a normal
For uniform and symmetrical, yes, it's a mirror reflection of uniform. Yes. Okay, so this is our algorithm. Generate uniform number, apply ln, divided by minus lambda, and this fellow will have exponential distribution. Okay, suppose you want to prove it. Suppose you say why, how it can be. Okay, you can take this guy and investigate it and find its distribution function. Okay, let's find distribution function, not now, of this guy. And you will see, you can do it at home on your exercise. And you will see the distribution function of x is exponential. Okay, you need to check it. You need to do it in home.
Like to do an inverse to do inverse.
Yes, it kind of, yes. And if you don't understand it, But you can also try simulation. You can say to computer, implement this. And we can draw histogram of x. And we can to look if it's similar to exponential random variable. Okay, I did it. Sometimes this is R code. We generate uniform 0, 1 random variable. We apply logarithm here, divide it by minus lambda. I generate here many points. Don't remember 1,000 points, and build the histogram. And it's very similar to exponential random variable x2. Okay, you have similar exercise in your homework, so you will need to read it to understand it and to write it in your own words. Okay, but it's very important for simulation, Monte Carlo algorithm. So it's very good exercise. Okay.
But
Okay.
people,
Yes.
it's very important that we always need to generate the uniform distribution from 0 to 1. It's because of we want to keep the probability between 0 to 1.
It's not super. No, you can also know 0 for 10, but usually it's 0 from 1 because you want probability from 0. But you can also use from 0 to 10. But you need to change this.
But always uniform the distribution.
Yes, and generally, not always, but in many situations, we generate some random variable from uniform 0, 1. Yes. And here you can read if you want. It's from simulation course how we can generate some discrete random variable from uniform 0, 1, how we can generate Bernoulli, binomial random variable. You don't have, yes, but if you're interested. Yes, how we can generate Poisson random variable. Generally, students study this material in simulation course and the next statistical methods. Okay, so this week we stop here. I won't publish new homework. Submit your homework number 3. I will publish solution to homework number 2 and continue next week.
Did we have the solution for homework number 1?
Yes, before 10 years, yes. Yeah, look, yes, good question. Just a moment before we stop. Let's check. Okay, thank you, Mohammed. Okay.